All right, hey, welcome back to Mechanical Pros. Here with Jeff Smith. Jeff, great to be with you again.
Great to be here.
Yeah. Today we got a good one. We're talking about motors, how to wire up a standard induction motor, primarily for a reduced voltage application, right?
Correct. We're going to go through a couple of different ways for reduced voltage, John. We're going to do both part winding start and Wye-Delta. But what I wanted to show you first was a standard 9-lead motor.
Yeah.
Not all motors come from the manufacturer with 9 leads. The way that you'll get a motor delivered is you'll either have 3 leads, 6 leads, 9 leads, or 12 leads.
Yeah.
If you'll notice, they're in multiples of 3-phase motors.
Yeah.
So this particular motor that we're looking at right here.
Can I tell a story?
Yeah, go ahead, tell a story.
So I first met Jeff on a job site in the middle of nowhere, Tennessee. I think it was about a 200 horsepower pump motor.
It's very large.
We had it wired up wrong or something, and it was running really hot, and we couldn't figure it out. We knew Jeff was the local motor expert. Called him out there, and he basically told us we had it wired wrong.
And motors are dumb animals. I mean, they respond to how you connect them. And so there is a specific
Or they don't
way.
respond to how you
Or they don't. Well, no, they're going to respond, and the response can either be good or bad, one of the two.
Exactly.
So, like I said, this motor here is what most air handlers, cooling towers, standard applications are going to see this type of motor, John. It's going to be a 9-lead motor, and this is called the terminal block. This particular motor here is a 9-lead motor, and so what this is dual voltage. It's suitable for both for 208, 230, or 460 volt connection. And when we pull in our connection diagram here pretty soon, we'll walk through that. But I want to go through what you need to look for when you walk up to a motor so you have a good idea of what you're dealing with and know your starting method.
So I opened up the pecker head and I got, we got 9?
We got 9 leads.
We got 9 leads coming out,
right?
And it's always intimidating.
Yes.
Because you don't know where you're going to land all those.
You don't know how to.
Leads.
You don't know where to connect, and that's why it's important to know your starting method too. Because what we're going to talk about today is electromechanical, and electromechanical is kind of an antiquated technology, but it's what we had before. But we still see it. Our service techs still see it, and so we all have to be on the same page on how a motor is to be connected. Now, this particular motor, 9-lead motors, are not suitable for reduced voltage starting.
So let's go back. Electromechanical was the old school way of doing a soft start.
Yes.
Right.
Yeah, and the reason why we have to do soft start is the building only has so much current allocated to it. And so some of the larger motors that you run into, a motor when you start it across the line is going to draw 7 times nameplate. So what we try to do is we try to reduce that inrush current by reduced voltage starting. Electromechanical only got us to about 4 times nameplate, but it was enough that we could still manage a building and not eat up all their power and dim all the lights whenever a motor would start. So it's nowadays we have electronic soft starts, we got variable frequency drives, all of those things take care of that soft start mode, but you're still going to run into electromechanicals, especially on chillers. We see it a lot on chillers.
Yeah, absolutely.
So when you first walk up to the motor, there's some information that you need to gather, and you need to know what your starting method is. If your starting method is an across-the-line starter, then you're going to hook this motor up a certain way. And if you'll notice on the top, now not all motors have this, so that's why you need to know the numbering system and how to connect for what voltage you're at. But on this particular motor, Baldor puts a sticker on here, and this sticker will give you both low and high. Low voltage is always considered 208, 230. High voltage is always considered 480. So it tells you how to connect the motor and tells you which motors are line and load. The other thing that you want to take a look at is take a look at the nameplate. On here is your rating. It's going to give you your horsepower rating, the amount of current that the motor is capable of. So that right there is the pertinent types of information that you need to have. Now, if your starting method is a soft start, we're going to hook this motor up across the line. If your starting method is a variable frequency drive, we're going to hook this motor up across the line.
Right, because your drive or your soft start's taking care of that.
They're taking care of that reduced voltage. This particular motor, 9-lead motors, there are some 9-lead motors by other manufacturers that are capable of reduced voltage, electromechanical, but you really need to refer to the paperwork from the
manufacturer. And if you do have a soft start or a VFD, and you do a reduced voltage wire at the pecker head, you're jeopardizing your motor long term, right?
Oh yeah, you're definitely going
Because you're not getting the full juice out of it.
Right. So what you want to do is remember, reduced voltage is just like that. It's the same physics law. Reduce voltage, lower the voltage, the higher the current.
Yeah.
So we want to move that voltage up to the highest point that the motor is rated for as quickly as possible, but still get that soft start.
Yeah.
Variable frequency drives do it a little bit different because we vary the frequency and the voltage. I can run at reduced voltage and not draw higher than nameplate. Soft starts, no. Soft starts are just like electromechanical. All it is an SCR that spins from 0 volts to maximum volts.
Okay.
It's like a variable voltage transformer.
All right. So if you have a drive, you got a soft start, you're always wired it up for across the line.
Wiring it up for across
All
the
right.
line, just like what you see here on the wiring diagram.
Okay.
Now what we're going to show you here in a second is we're going to show you different starting methods, electromechanical, and then we're going to tell you only certain motors are capable of doing that. They have to be rated for soft start or for part winding start or for Wye-Delta. And you're always going to be able to tell. If you have a 6-lead motor or a 12-lead motor, they are always going to be suitable for part winding start. If you have a 3-lead motor, obviously, no, you can't. Okay, 3-lead motors are usually going to be single voltage. They're not going to be dual voltage, and they're only good for with soft starts or variable frequency drives.
Or across the line.
Or across the line.
Right.
Yeah.
We got a wiring diagram here, huh?
We have a wiring diagram, and I want to make sure that everybody understands, some of the stuff that we're looking at. On the drawing itself, this would be your main circuit breaker. This is a three-phase ladder diagram, so I want to make sure that everybody understands what we're looking at, John. These are contactors, and if you've stood in front of these before, this is a 3-phase contactor. Now, in part winding start, we use 2 of these. Okay, and in between the 2, and I didn't do the control circuit, if that's for another day, but basically what happens is when we do part winding start, the 1M contactor is going to come in first, and that's going to connect my leads 1, 2, and 3. What that essentially does is it gives me 68% performance of that motor winding. And so what I'm trying to do is I'm only using 68%. I'm getting to about 4 times inrush current. As soon as I see the inrush current start to drop off, there's a timer in the control circuit that will go ahead. And once I establish when that happens, I set that timer for usually 3 to 4 seconds. It will go ahead and close the 2M contactor and bring my other side of my winding. Now what's important is you need to understand that this is on a 6-lead motor or a 12-lead motor. So what I've done is I've given you across the line connections. If I was going to start this 6-lead motor across the line with a single contactor, I would connect that motor. L1 would be motor leads 1 and 6. L2 would be motor leads 2 and 4. L3 would be motor leads 3 and 5. Okay? And those motor leads are numbered. But what we have to remember is that I have to stay in that configuration. So if L1, if you look across along the bottom of the contactor, okay, 1, 2, and 3 are correct. It's left to right, 1, 2, 3. But when we go over to the second contactor, remember leads 1 and 6 have to be on phase A. So if you notice, phase A comes in.
So we got 1 here, right?
Right, L1.
And then we got 1 and 6.
1 and 6.
They're going to come up.
And they're going to hit 1
right there.
Right. And then 2 and 4 will connect, 3 and 5 will connect.
Yeah.
Just like what we have for the across the line. So what happens, like I said, we're at 68%. When I bring the 2M contactor, now I'm going to go ahead and get full voltage to that motor.
Okay.
Okay. Even though there's 480 here.
So M1's coming on, are all 3 of these?
Yeah, all 3 of these close at one time.
Okay. And that you're saying that's 60?
That's 68% of the motor winding.
Motor windings. And these are going to come on, and there's going to be a timer, and then 2M's going to come on.
Right, and then we bring in the rest of the winding. And then that gives me full torque, full current.
Okay.
Okay, so this is what we call part winding start. Now what's important is that you can either do 6-lead motors or 12-lead motors. Now when it gets into 12-lead, it gets a little bit more concerning. And this is generally where we run into an issue with field personnel. Because they get a 6-lead motor, hey, that's easy. That's T123, 645, okay? They'll call me and they'll say, hey, I got a 12-lead motor. I don't know how to connect this. Well, we know that if you'll take a look at our 12-lead across the line, our 12-lead across the line is 1 and 7, 2 and 12, and 2 and 6. So how would you connect that, John?
So I had 12 leads?
Yeah.
So I'd have to draw, I need to add some leads.
Yeah, you need to add some leads to both
Yeah.
of these, right?
Yeah.
So what I would do is I would go T1,
T1, the
T7.
Yep.
right?
Yeah.
And then I would go
12 to 6.
T6, T12.
Yeah.
Okay. And then on the second one, I'd go T8.
Yep. And then
And
10.
then T what?
It'd be T10, the T4.
T10, correct?
Yep.
Okay, so that takes care of that side. And then T3 would be
T9
T9,
and T11.
T11. That make sense to you?
Yeah.
Okay, so I'm basically doing the same thing part winding start. I'm just adding 6 more leads to it.
Yeah.
Okay. And what you have to understand.
You're just combining them in the equidistant.
Right. Right, because the 12 lead motor, I still want 68%.
Yeah.
Okay, so in order for me to get these 68%, I have to make, these 2 wires have to be together, okay, because they're on one series of coils, these are on one series of coils, these are on one series of coils.
Okay.
Because the way a motor winding works, it has a series of coils. This is the either side of one set of coils. Same thing with T6, T12, T4, T10. And if I was going to run it across the line, I would hook it up like that. So these connections that you see here are these connections that you see here. Mm-hmm. Okay, and those are all grouped together. Connections are made at what we call the crown, and then it comes out of the pecker head of the motor, and it numbers them 1, 2, all the way through 12.
Okay.
Okay, so
we're gonna get a great diagram.
yeah, we'll get a great diagram. But what's important here is to understand the connection to the numbering system, because this is where our guys in the field, I mean, you sit there, I mean, you opened up that motor, you look at it, you got a bunch of open leads and a bunch of numbers, you got no idea how to connect it. So when they walk up to a part winding start, like what they see here, 6 or 12 lead, they're gonna know how to do that simply by doing this. Now, we talked about a 9 lead motor. Okay, a 9 lead motor was just like what we opened up over there. So what I've done down below here, I've given you standard dual voltage connection tying leads together. Okay, and if you'll notice, ACL stands for across the line. That would be just a contactor and an overload. And so L1 would be T1 and T7, T2, T8, L3 would be T3, T9. And then you tie motor leads 4, 5, and 6 together. This is for either 208 or 230, this is considered low voltage connection. Cross the line starting, variable frequency drive, soft start, whatever, that's how we would connect a 9 lead. If we go to 480 volt, lead L1 is going to be motor lead number 1, L2 is going to be motor lead number 2, L3 is going to be motor lead number 3. But now what we do is we have to make some other connections. Tie 7 and 4 together, cap them off. Tie 8 and 5 together, cap them off. Take T9 and T6 together and cap them off. And what I mean by capping them off is you isolate them and they never see voltage. I don't apply voltage to those leads, okay? Now, motor connections are a little bit, NFPA 79 addresses this. It's NFPA 79 2007, and it's clause 13.9.5.2, if you ever want to look it up, okay? And what that tells us is it says it must be an identifiable connection method. Twist-on wire nuts are not an acceptable method. This is what we refer to for motor leads. Wire nuts are great in control circuits and house wiring and that type of stuff. Motor leads are a varying current of which they can get hot. There's a lot of things. So even NFPA they've recognized, hey, don't use wire nuts on motor connections. Now, on small motors, John, we've gotten away with it.
Yeah.
Okay, but when you start hitting that 5, 7.5, 10 horsepower, you know, really start looking at that. And so acceptable methods are going to be like Polaris lugs, ring terminals with a machine screw through it and a nut and then rubber tape and 33, you know, or split bolts, you know. So those are the kinds of things, and especially when we're connecting this up, absolutely, positively never use wire nuts. Always use an acceptable connection method.
Yeah.
So that kind of covers our 9 lead and our part winding start.
Just what would you say the percentage of motor failures
70.
due to wire nuts?
Yeah, due to wire nuts. Because wire nuts create loose connections, and remember, motors fail in patterns, just like anything else. And you can tell immediately how a motor failed. So when I worked in the motor shop, I used to do the postmortems and try to determine cause of failure. I had to do root cause. Well, the minute I'd open it up, if 2/3 of the winding was burned up and 1/3 is pristine, first thing I do is go look at the pecker head and see how they connected the motor, because that's a single phase condition. So that's usually what will happen is you'll get uneven current that'll draw through the motor and cause the motor to burn in that type of pattern.
That makes sense.
So it's probably 70% of our calls that we get, like I have our guys, our service techs, you know, the minute they get out on a job site, the first thing they're doing, even on our new construction, they're opening up the motor pecker head and looking at connection methods.
Yeah, we do now.
We do now.
Yeah.
Yeah, because we learned that, you know, that's going to be your number one callback.
Yeah, since I called you that time.
It's going to be your number one callback. It's always going to. That's the first place you go. Work backwards.
Yeah.
So.
I love it. I'd love to cut one open that we know is burnt up.
Yeah, and one of these days when we get one in here, we'll do a postmortem on it, and I'll show you what we go through.
That'd be great.
But it really is motors are, like I said, they're a dumb animal doing a very specific role.
Well, you order the wrong motor, you can make your job really hard.
You can make your job very hard. You order a 9-lead motor and it's a part winding start or a Wye-Delta, good luck with that.
Yeah.
It's just not, there's some motors you can, some 9-lead motors you can, but you need to refer to manufacturer specification on how to connect that, because they will give you, it's not going to be consistent manufacturer to manufacturer. Okay?
Okay.
So that kind of covers part winding start and across the line. So what we're going to talk about next is Wye-Delta, John, and the reason why I want to take a little bit of time on this one is this is the one that really causes a lot of issues in the field.
Okay. All right, Wye-Delta.
Wye-Delta, this is, like I said, this one here is the one that really kind of scares you when you walk up to it. Now remember, in part winding start, we had a 2-contactor system. Well, when we do Wye-Delta open transition, it's a 3-contactor system, okay? And what we have to do is we have to start on the Y part of the winding. Remember before we were splitting it up 68%, I was only connecting one side. Now I have a definite differentiation inside the motor between the Y and the Delta, okay? So we start on the Y, and again, like I was saying, this is your main circuit breaker, and if you'll notice we have 3 contactors that go across here. The 1M contactor is going to come in, but in this case, John, like the part winding, we're also going to bring in the shorting contactor because I need to short the Delta. Now what this does is it gives me a much better reduced voltage performance. So before, when we were at 4 times nameplate, now I can get down to the 2 and 3 times nameplate on startup, okay? But we still have a timer in the circuit, but what we add is we add a mechanical interlock, okay? So these 2 contactors have a mechanical device in between them that if one is in, the other one can't come in, even if you have voltage applied to the coil, okay? So
with the timer?
What happens is 1M and shorting contactor come in first when you send a start command. It times out. When it times out, it drops the shorting contactor out of the circuit and then energizes 2M and connects the rest of the winding. Now, if you'll notice, my leads are a little bit different on this one. I go 1, 2, and 3, 7, 8, and 9. Your first question is on part winding start, why did we have to go 6, 4, 5 out of sequence? And on this one, we can do 7, 8, and 9. The motor is connected differently internally. That's why we do 7, 8, 9. And if you'll notice on my 6 lead across the line, line 1 is T1 and 7, line 2 is T2 and 8, line 3 is T3 and 9. Whereas before it was 1 and 6, 2 and 4, 3 and 5. This is 1 and 7, 2 and 8, 3 and 9. So we are in sequence, and my polarity is the same inside there because I don't have to use half the winding, okay? So what I do is I short out the Delta during startup. I only use this portion of it, and it runs a little bit. Timer times out, drops the shorting contactor out, and brings in the 2M contactor. When I am in running condition, both these contactors are in at one time.
Jeff, let me walk through this again with you, just make sure I got this thing straight. So here's we got our supply. We got the M1 contactor. We got T1, 2, 3. We're going to energize this and get the motor spinning.
Right, but we have to short the Delta.
Right, yeah. We got to short that Delta.
Yep.
It's really a false Delta. It's not truly faulting or shorting the motor. And then once we get inertia and the interlock times out, then we open that short, and then we're closing the M2.
Correct.
And we're able to get full current
At that point
and capacity out of the motor, but it's a much reduced inrush current because we got that motor started and then the momentum's already going.
Right. What we're doing is we're calculating when we want to apply torque.
Yeah.
Is what we're basically doing, and we're doing it through timing.
Okay.
Okay.
And I hear what you're saying. So if you're building like a commercial office building and your chiller's like the largest, by far the largest motor, you're going to have nothing else nearly that size. You don't want to oversize your whole system just for that one motor.
Just for this, just for the chiller.
And so let's not have all that inrush current.
Right.
And let's start it slowly. And this is the way to do that.
Right. And when we used to build buildings, John, I mean, that was the way all of them were done, because we didn't have soft starts and Wye-Deltas, and so these starters were massive.
Yeah, I can see how this could be really intimidating to a guy on the site.
Oh yeah.
He's scared to try it.
Yeah, I mean, it really can be, because really it doesn't take much
That's a religious experience.
Yes, it is.
Yeah.
It doesn't take much of a mistake to cause a flame.
Yeah.
And when you're talking about currents in the 1200 amp, 1300 amp range, it can get really ugly really quick. So we want to make sure that we connect our motor correctly, because not only are we going to damage the motor, we're also going to damage our components. We're going to fry the contacts and the contactors, and they have to be replaced. And so it's really, really important that you pay attention to this. Now, most chillers that we deal with are 6 leads, but we do have 12 lead. And so I wanted to make sure that we got together and talked about a 12 lead Y-Delta. Okay, so I did the same thing with this, John, just like I did with the 6 lead across the line. I went ahead and gave you an across the line for the 12 lead.
So we'd add T12 to this.
Right.
Right?
We have to add T12.
T12 to T1.
Right.
Right. And then we're adding T10 to T2, and then 11 to T3.
Right. So that's basically what you're doing.
And then we're capping these.
And then what we're doing is we're bringing T4, T5,
and 6.
And T6. And then over here, we're doing...
Yeah, write that. We got 12,
T12.
10, and 11.
We're doing T10, T11, oh, excuse me.
Yeah, that's not 11.
11. Okay, so what you have is just like my across the line, okay, but the only thing I haven't done is, you see how these are together and capped? What I said is, all right, now we're not going to cap them. We have to have them in the circuit now because I'm Y-Delta. This is why Y-Delta gets really confusing.
Especially when you're right together and capped.
Exactly. If I'm running across the line, I'm going to be together and capped. So this is why Y-Delta becomes really important when you're hooking up a 12-lead motor on a Y-Delta starter. Thank God we don't see a lot of them anymore.
Yeah.
But this is what you have to be very careful with. And so the thing I'm trying to get across is, we need to make sure of your motor leads, the type of motor leads that you have. Do I have 6-lead? Do I have 12-lead? Do I have 3-lead? Do I have 6-lead? 9-lead? So those are the things that you need to know before you ever start connecting and hit a start button. Because there is no coming back, okay? Now, obviously we have circuit breakers and everything else that we hope will clear, but sometimes they don't, John. Sometimes that current is so quick, it'll go ahead and exceed the rating of the contactor.
Yeah.
Okay? So hopefully I kind of cleared up some of the connection methods that we use. Nowadays, we don't see a lot of it, but your service techs are gonna.
Yeah.
And so this is what we call an open transition. There is a closed transition version that we use in chillers. It adds another contactor and a set of resistors. I didn't draw that out because it can get real convoluted real quick.
I never understood the short the delta.
Yeah. It's what I'm doing is I'm telling it you're a big block of copper.
Yeah.
I don't want you to do anything. I just want you to sit there and magnetize.
Yeah.
That's all I want you to do. And then when we get done, we release that. We bring the second half of the winding in. Make sense?
Yeah. How critical is the timing between your Y-Delta releasing and then your 2M.
Well, it's very critical.
Contacting.
Yeah, what you don't want to do is you don't want to have it too long, because remember, I'm not starting with the full winding. So if I start that load or I start that motor and I start picking up load and I don't transition and bring the rest of the winding in, I'm going to overcurrent half that winding. Okay, so generally the way that I have our guys set it up, put your amp probe on either line 1, 2, or 3. Sit there and measure it. When you see the current start to fall off, because when you start it, it's going to come up. When you see the current start to fall off, that's when you want to make that transition.
Yeah.
That's when we set the timer. But it's very critical, and there's no risk of us, unless the mechanical interlock is broke, there's no risk of us, shorting the starter out, because this won't allow this to come in unless that is fully disengaged.
Yeah.
And then it comes in.
Okay.
So I kind of float free for a second.
Yeah, I get it. That helps me.
Yep.
Yeah, I'm gonna go see it in the field.
Yep. And hopefully it helps the guys in the field. And like I said, if you guys have any questions, give us a call. We'll walk through it. Some of the stuff that we went through today, I know it's a lot, and not all motors are the same.
Yeah. Hey, thanks for checking us out, Mechanical Pros. Thanks for hanging out with me, Jeff.
Thanks for having me, John.
Yeah, and if you guys got questions, comments, please put them in the comments, and hit that like, hit the subscribe, and come back, check us out, and we'll see you again soon.